So the reason we decided to present together is because those papers are based on a foundation of stats. So we'll start with a general background, so we don't have to do it twice for both presentations. So these are the two papers. So like I said, the first part will be sort of a crash course on probabilistic response surface, cross-correlation, and spatial variability. Okay, so first, what is probabilistic analysis? Or what's the difference between deterministic and probabilistic? So for deterministic analysis, say you have cohesion, which you're trying to input into your analysis. You can only input one value, 2 kilopascals, for example. And from that one input, you get one output, factor of safety. With probabilistic analysis, instead of the single input, you input a distribution of cohesion. So for example, in this case, you have a distribution with a mean of 2, which ranges from 0.5 to 2.5. And then you sample that distribution, say 1,000 times. And then you use, for example, a cohesion of 0.7 in simulation 1, cohesion of 2 in simulation 2, and so on. You do it 1,000 times. And at the end, you get your probability of failure, which is the number of simulations with a factor of safety below 1 from that 1,000, divided by the total number of simulations. And in addition to that, you also get your regular factor of safety value. So like Dr. Bather said, you're only gaining more knowledge. Okay, so this will go sort of jump around very quickly. So the next topic is stochastic response surface. So stochastic response surface is one of the sampling methods you can use to get your samples from that distribution. It uses a primitive form of machine learning to create a factor of safety function. So the main advantage is that it gives you the probability of failure much faster than if you did it with Latin hypercube or Monte Carlo sampling. And this is best explained with an example, so I'll just dive right into an example. So this is a slope with 2 random material variables and 1 random load variable. So 3 random variables in total. The specifics are found here, such as which search method we're using and so on. And basically, we can either compute this with Latin hypercube, which is just a traditional sampling method, or we can do it with response surface. So what response surface does is, instead of computing all 1,000 simulations, say, it computes a small number of representative samples. So like 20 or 30, depending on the number of random variables. And it uses that to train a function which can predict the factor of safety. So for example, in this plot, for the model that we showed in the previous slide, the blue line is the actual computed factor of safety for simulation 1, for example, whereas the response surface is the one that predicts that factor of safety using the function we train. And you can see that the true factor of safety versus the predicted factor of safety, they're very much in agreement. Some outlier cases can be seen when the values are extreme, but for the most part, it's very, very accurate. And so what is the advantage of this? Computation time. So in the first case, we did 1,000 samples with Latin hypercube. The probability of failure was around 73%, and it took about 7 minutes. This is a simple model. And for the second case, using response surface, again, we got results for 1,000 samples, but we only actually computed 40 samples and used those to train our response surface. The probability of failure was about the same, 73%, but the time was only 0.3 minutes. So basically, we got the same result in 4% of the time. Okay, so that was stochastic response surface. The next topic we're going to abruptly jump to is cross-correlation of parameters. So the other thing you have to consider when you're doing probabilistic analysis is that parameters are correlated. So say you have, you're looking at simulation 1 of an analysis where cohesion and friction angle are random variables. So you have those two distributions, which we looked at before. So if you just randomly sample the cohesion distribution and the friction angle distribution, then you might end up with a very low cohesion value and a very low friction angle value, which of course is not something we typically see in the real world. So you wouldn't want to consider that simulation to be like, to have the same weight as a more realistic simulation where a high cohesion is matched up with a low friction angle. So that's why you would input your correlation coefficients to ensure that high C and low phi are matched up in each simulation. Okay. The next topic is spatial variability. So the method we've described so far is called single random variable approach. So that's the one we showed in the first slide, where basically the cohesion value that we sample is assigned to the entire slope for that simulation. So basically, there's a big assumption that the slope is homogeneous, which means we're saying that cohesion at x equals 0 is 0.7, and cohesion at x equals 100 meters away is exactly the same, which is not very realistic. And that's where spatial variability comes in. So using the single random variable approach, simulation number 1 might look like this, as we showed. So the same cohesion throughout. Using spatial variability, simulation number 1 looks like this. So the slope is divided up into cells, and a different sample from that distribution is assigned to each cell. So this is more realistic of what you might see in real life. And then similarly in simulation 2, in the SRV approach, you assign a different cohesion to the entire slope. With spatial, you generate a different random field. But of course, it's not as simple as just saying, cohesion here is 50 and here it's 1, because probably you wouldn't see such a drastic transition in real life. So that's where the correlation length comes in. So correlation length describes over what distance are the parameters similar. So in the deterministic case, the correlation length is infinity because cohesion is the same throughout. Similarly, in the SRV approach case, correlation length is infinity because we assign the same cohesion value throughout. If, for example, in the spatial case, we set a correlation length of 1 meter, then what we're saying is that within 1 meter chunks, roughly, that's how much distance it takes for the cohesion to change. And if we say, for example, correlation length is 20 meters, then we're saying within 20 meter chunks, the cohesion values are similar. And you can see the difference in the field when you look at correlation length of 1 versus 20 as well. There's larger pockets of similar parameters. Okay, so now that we have a general foundation, we can move to the actual content of the papers. So the first paper is called A New Stochastic Response Surface Method in Spatial Variability Slope Stability Analysis. Basically, the aim of this paper is finding a response surface method that works with spatial variability. So spatial variability has gained a lot of popularity in recent decades. But the response surface method, which predicts the factor of safety, can't really be applied to spatial variability. And I'll explain that in the next slide. So in this paper, we proposed a new method that works with spatial variability that uses variational autoencoders, which are used to compress things like images. Okay, so as we talked about before, traditional stochastic response surface basically does this. So F is the factor of safety, and factor of safety is defined as some complicated function of the random variables. So if, for example, the random variables are cohesion and friction angle, and we're looking at an SRV analysis, not a spatial one, then factor of safety is a function of the cohesion sample and the phi sample, so two variables. But when you look at spatial variability, instead of two variables, you now have 2000 variables. For example, if you have 2000 cells, each cell is a parameter that has to be considered. So traditional stochastic response surface becomes infeasible. Basically, it would take way longer than actually just running a Latin hypercube or Monte Carlo. So a new method is proposed here called the variational autoencoder method. So the way this works is it uses something called a variational autoencoder, which takes the original field, which might have 1200 random variables, for example, 1200 cells, and it compresses it the way you would compress an image to a more simplified version of that field. And this field now has 48 variables. So what does that mean as far as the response surface is concerned? Basically, instead of trying to deal with factor of safety as a function of 1200 variables, the 1200 cells, we can now define factor of safety as a function of 48 variables. And then just to explain, so what is the difference between this method and the traditional response surface method? So with the traditional response surface method, you compute your n representative samples. Then you generate the coefficients of this factor of safety function using that small number of samples. Then you plug in all the samples that you actually want to compute the factor of safety for, and you predict the factor of safety for each of those and get probability of failure. Meanwhile, with the variational autoencoder method, you start with computing your n representative samples. Then you generate the coefficients of factor of safety, the factor of safety function. And in this case, it will have, if cohesion and friction angle are random variables, 48 times 2 parameters. Then you plug in the compressed versions of all your desired samples. So you pass all your desired samples through the autoencoder and plug them in. That predicts the factor of safety for each simulation, and then you get the probability of failure. So the results, we've computed a bunch of models, and for the most part, the results we've seen are something like this. The probability of failure might be something like 0.5 in Latin hypercube, 0.7 in the variational autoencoder method, but in something like 1% of the time. On the other hand, we've seen some outlier cases, so this method still needs some work, but it's brand new and very promising. So yeah, we encourage anyone to study it, and we're going to keep studying it as well. Okay, and now I'll pass it to Sina for the second paper.
Thanks, Brigid, for the first part. It made my section easier. So I'm going to talk about probabilistic analysis of a slope using a random limit equilibrium method and cross-correlated conditional random field, which Brigid explained a lot of part of it, and I will just continue using the terms that she used. So, but I would like to start with something that it's very important, and Richard talked about it as well, the reluctance in adopting probabilistic analysis. Why people, engineers, they don't like to adopt probabilistic analysis. First of all, as a civil engineer or mining engineer, our knowledge is very limited in training in probability theory. Someone like Brigid can go and study statistics in at university if you are very interested, but we only pass one course in our bachelor degree. And that's why we are very comfortable with deterministic analysis, because it's just one factor of safety value, and that's it. It's very easy. And there is another misconception, is that probabilistic analysis requires a lot of more data, time, and effort to be carried out. And you saw Richard's presentation, with one equation, you can even find the probability of failure. The other problem used to be, before we released a slide to 2018, which there was no really good software, commercial software that can carry out probabilistic analysis considering a spatial variability. Because if you don't consider spatial variability, you may have wrong results. And the other concept is that probabilistic analysis is not a replacement for deterministic analysis, and they should be used together. So mentioning these, the other thing that Brigid presented was about the spatial correlation lengths. This is another example that you have horizontal correlation lengths of 20 meters and vertical correlation lengths of 2 meters, which is the typical ratio of these two parameters, and you can see it in the real field. But where do we get this magical parameter? So, and that's the other thing, engineers, they are more comfortable with deterministic analysis because these terms make things more complicated. But luckily, one of the data that we used for measuring this correlation length is CPT data that is available basically in every project. And we published a paper with Dr. Poon and Ching and Brigid, and we have several tables that suggest different typical values for correlation length. But in general, you can use different methods to measure correlation lengths using CPT data. The most recent one, advanced one, is the Bayesian method that we use in this study to measure the correlation lengths. The other thing that I wanted to talk about is random limit equilibrium method, which is the method that we use in this study. Basically, it's a combination of random field theory and limit equilibrium method. And Richard and myself, we named it random limit equilibrium method in 2017. And it's very important that you know that this is a simple limit equilibrium method and you can put it on top of a random field. But be careful, because if you look at this failure surface, it is not a typical circular limit equilibrium method. Luckily, when we released the slide to 2018, we added an advanced method called surface altering optimization that Terence is going to talk about it probably today in his presentation. So this surface altering optimization finds the weakest failure path that you can see. The blue region is the weak region, and the critical slip surface goes through this weak region. And to emphasize that this is limit equilibrium, you can see these slices. We did one more step for the limit equilibrium analysis, and we started to sample at the base of each slice, like 10 times, to make sure that the results are more accurate. So we have 50 slices in a slide as a typical number of slices, but for the spatial variability analysis, we basically have 500, 10 times at the base of each slice, we do sample. The goal of probabilistic analysis, though, is to reduce the level of uncertainty of the problem. So how can we do that? The traditional probabilistic analysis, which Brigid mentioned, single random variable approach, consider a very large uncertainty, but there are three more steps to reduce this uncertainty. One is considering a spatial variability of soil properties, instead of assuming that every sample is homogeneous. The second one, Brigid explained, is considering cross-correlation between soil input parameters. And one more step is considering the available data to generate random field, which is called conditional random field. There are so many methods to condition the fields. The most recent approach is introduced by Ching and Poon in 2017 and Ching et al. 2021. They use a sparse Bayesian approach to provide site characterization and conditional random field. These are too much for engineers. So what we are trying to do, and we are adding this feature to rock science software, is this method and this code only gets CPT data, and it measures everything automatically. So basically, it measures mean, standard deviation, and spatial correlation length, and get the cross-correlation parameters, and at the end gives you a cross-correlated conditional random field, which is the goal for engineers, because they have CPT data, they don't know what are their mean, standard deviation, and their parameters are, and they use this code and our software to just get the random field. And that has a lot of practical values, and we are trying to make it practical for engineers. We are trying to make spatial variability analysis more practical. So what is the conditional random field? Basically, let's say these three lines, vertical lines in my model, are CPT lines. Basically, we know the values of these lines along these vertical lines for each parameter. So we don't really generate random fields. They are not 100% random anymore. We use these CPT data to condition those fields, to say that, okay, we know the values of these points, and we generate fields that they have known values at these locations. So here is a procedure that we got it from Sassanian et al. For this study, we didn't have any CPT data. So we randomly generated an unconditional random field for friction angle. Then we extracted artificial data points along the vertical axis in at different locations with 5 meter horizontal spacing and 0.2 meters of vertical spacing. And then we use the data, these artificial CPT data that we generated, to condition our field for friction angle using Bayesian approach. And then we assume the mean and standard deviation for cohesion. We assume the cross-correlation value between cohesion and friction angle, and then we generated conditional random field for cohesion as well. So we started friction angle. We know the relationship between the cross-correlation and the mean and standard deviation of cohesion and friction angle, and we generated conditional random field for cohesion as well. So this is one example of the points that we measured for friction angle. These are the statistical parameters that we measured based on the field that we had. And then we assume these parameters for cohesion and cross-correlation between cohesion and friction angle. And then we generated the cross-correlated conditional fields for cohesion. This is the example model that we got from Dasbach et al. 2022. And this is one example of unconditioned friction angle. Then, as I explained, using the procedure that I mentioned, we condition the field for friction angle. And then we use this field and the parameters that we assume for cohesion to generate conditioned field for cohesion. And to see if they are cross-correlated or not, you can see, for example, this red region corresponds to a blue region from friction to cohesion. So basically, low values of friction angle corresponds to the high value of the cohesion and vice versa. To check if our method is working or not, we measured some data. We extracted some data from the conditioned field and compare at the same location that we condition our field, and we compare to our original data that we use to condition the field, and you can see that they are matching perfectly. This is for one of the locations. We had like 10 of these location points. In terms of the results, for this model, the deterministic factor of safety was 1.1. When we had unconditioned spatial field, we got the probability of failure of 7.6%. And when we conditioned our field and cross-correlated with cohesion, we got the probability of failure of 1.2%, which is about 6 times less. And if you don't assume a spatial variability in general for this field, you're gonna give way higher probability of failure. So these values are with a spatial variability unconditioned and conditioned. And you can see the conditional field reduces the level of uncertainty, means that it reduces the probability of failure. So that's about our presentation.